Yeah, hello. So I'm Linhao. I'm currently a postdoc here at KITP. I also jointly have a position in Princeton, but they're not paying me this year. So I'm going to talk about the spins of binary black holes from isolated binary channels. So we already hear about the spins of them from FOIA in these dynamical channels, but how about if you actually have binary stars that are working? So this is a work in progress with these very smart people. Okay, so to start, I'm going to, once again, asking for attention to this thing that you have already seen a lot of times. So this is basically the isolated binary formation channel to have merging binary black holes. So we already heard about a lot of physics going on here. But we haven't talked about the spins like very much, like in this conference. So the basic idea is that you have several physical processes that's going to control the spins of the final black holes. So you can have mass loss that removes angular momentum from either the star or the orbit. You can have some internal angular momentum transporting stars that actually redistribute your angular momentum in your star and decide that whether if you lose it, like if you lose your envelope, how much spin you get lost. And you can have accretion that may change the spin of stars or combat objects. And you can have tides, if they're close enough, that's going to transfer angular momentum between the spin and the orbit. And you can have collapses. I'm not an expert on that, but I'm not going to talk about it today. So there are a lot of things going on here, but the first basic thing is that, at least for the first form black hole here, the thing that's going to matter the most is probably angular momentum transport. Because whatever is happening here, from this phase to this phase, you have a very expanded, slowly rotating envelope and a very fast rotating stellar core, which eventually becomes your black hole. So if you have very efficient angular momentum transport, so basically the result is that this spin, the spin of this black hole is going to be likely zero. So this is some work I did quite a few years ago. There's of course some debate on whether you should have this kind of angular momentum transfer mechanism. So that's a very hard problem. So I eventually gave up working on that. But let's say this is true. So we start from this stage, and then you have all of these, channels, and so there's a little things going on here. I'm going to talk about in my next slide. But eventually, if you after this common envelope phase or stable mass transfer phase, you eventually end up with a black hole with a helium star in a very tight orbit because your shrinks the orbit a lot. This means that tides can actually do something probably to this star, and when this star becomes a black hole, it's probably going to be rotating or not rotating depending on your setup. So I say that this could be common envelope or stable mass transfer, so I'm going to talk a little bit more details about that. So I move this part of the plot to here. So our knowledge up to a few years ago, mostly for these evolutionary phases, is based on this rapid binary population synthesis, which are fast, but usually you use very simple descriptions to produce that. So, for example, this is half the plot from a paper by Monica Gallegos-Garcia in 2021. And so the y-axis showing if you have this black hole plus star, and this is initial period, and this is the mass ratio if you fix the stellar mass and change the companion black hole mass. So these are sort of the results from binary population synthesis about how you can form merging black holes. But basically, it's this parameter space here, this orange channel, which says that you're mostly forming through common envelope. However, now we have massa and some more detailed, binary mass transfer physics. So actually, if you do massa models, and you are going to see there's not seem to be many common envelope events, right? So eventually, you can only form binary black holes through this stable mass transfer thing that is creating this part of the parameter space, which is like a banana shape here. So this is the thing I'm going to focus on because I think it's more likely. Another reason I already did this calculation before, but okay. So I'm going to take this parameter space. This is my plot of it. It's basically the same thing, but I remove all the binaries that are not very relevant. So this is 30-star mass black hole. So what I'm going to do is that I'm going to follow this evolution. I'm going to add a very up-to-date tidal torque calculation into those models, as I proposed before, and going to do some post-processing on this process to see what the spins will look like. So here's the result. I'm sorry, I don't really have time to talk about detailed tidal physics, but you have to believe me. So this is the result. So you immediately see there's an interesting trend, right? The color is showing the dimensional spin of the star, when it's like collapsed. You immediately see a very interesting trend. Well, but first you see a very boring trend, which is basically if you fix your mass ratio and you're moving to shorter initial period, then you have higher spins. This is all expected because you are in a tighter orbit, so you have stronger tides, right? The interesting trend here is that you see some high spin systems here, but you don't see very high spin systems here. This is actually in contrast to your intuition because those are actually, they have more massive companions, which should actually give you more tides, right? So to understand this, we have to look at some of these evolutionary tracks of these spin orbit evolutionary tracks of this individual system. So I'll just take two systems, for example. So this one I call it binary A. This one I call it binary B. So let's take a look. So to understand this mass transfer physics, first we take a look at a single star evolution. So this is the radius versus time over its evolution from the start of the main sequence to the end of the helium burning. So there are 3 panels, but that's only because I'm zooming in different stages because they're not happening on exactly the same time scale. So this makes it clear to see. So when you have a binary companion, you have a Roche lobe, right? And depends on where your Roche lobe is. It actually controls when you start to trigger mass transfer. So let's say for the binary A, so I call it case A here. And you can see that Roche lobe is here and it's filling. And it's Roche lobe here, and you do this mass transfer, and basically this follows the radius evolution. So for the binary B here, I call it case B, it's something like here. So you actually start mass transfer after the main sequence during the helium burning phase. So if you look at these individual cases and look at the angular momentum, so this is dimensionless spin of the star, but basically that tells you the angular momentum. You see that what is only important is actually after this kind of mass transfer phase, because whatever angular momentum accumulated here is going to be removed by this huge mass loss during this mass transfer phase, and eventually you have this tides working in this stage that gives you some spin. So the tides are only important after last phase, fast mass transfer phase. So for the case B system, you see that this is also true, but somehow you have higher spins. So what is the reason for that? The reason is that if you actually compare the radius versus semi-major axis in these two cases, so this is in log plot, so this distance basically tells you log A over R, right? And you realize that tides are actually a very strong function on A over R. So in other words, in the case A system, you have a larger, you have smaller, you have larger A over R, which means smaller R over A. So you have very weak tides. In other cases, you have very strong tides. So this basically explains all the systems we see. So I did these things for all the systems, and you can see that all the case A systems are here, and case B systems are there. Okay, so if we transfer that to the final chi effective versus the final black hole mass ratio, so if you care about mass reversal, this is also a color showing that. You can see that these case A systems are not spinning very fast, while this case B system can be spinning faster at a lower mass ratio. So this may already look very familiar to you, right? Because there's a claimed correlation, for this chi effective and Q anti-correlation, but actually this is not correct. The reason for that is because for this 30 solar mass star, they're very less massive, and all these high spin systems actually have primary black hole mass about below 14 solar masses. So it's actually not contributing to that population. Okay, I think I run out of time, but basically the intuition is that we look at these 50 more massive star plus black hole systems. And it turns out you can have some systems here that are rapidly rotating, and that's actually controlled by another phase where you only have case A without this mass transfer case. So you actually preserve the remaining of the angular momentum. So this is a normal case A plus AB case, So you don't preserve angular momentum here, but if you're moving to a higher mass, you can have spin here. And then you sort of work this out, and you have this correlation again, but now this high spin system from this case A only systems, and you can have this correlation, which is good. This is another one for even higher masses. Okay, I leave my takeaway here. So let's say you somehow have a star plus black hole, right? You don't care about those that are not merging binary black hole, and you go through all this process, and you can possibly have high chi effective or low chi effective, depends on your parameters. The takeaway too is that it's possible that just from isolated binary channel, you can have this negative Q chi effective, but it's very rare. It's only through these systems, which is a very small part of parameter space, which means that if you eventually don't find it, it's also consistent, but I'm not. Yeah. So, okay, thank you. So that's all my talk.
Linhao, thank you very much. We should have been talking the whole conference this week. Question, I'm sorry if you said it, are you allowing for super-Eddington accretion onto the black hole?
No, I don't care. I care, but I don't. Okay, I don't have, I don't know the physics about the accretion onto the first burn black hole and the spin of it. But my impression is that if you don't accrete, like almost a lot of its mass, it's not going to spin it out very fast. And that's actually found in these mass transfer models. Yes.
Yeah, that's why I'm asking.
Yeah.
Okay, all right, thanks.
So you mentioned, you talked about R over A or A over R, but as the determinant for spin, but it actually looked to me like your R is going to be the same, and so it's not really about tidal efficiency, it's about the separation of the binary, right? If you're tidally locked, what ends up determining the spin is actually what your binary separation is, right? So depending on the mass transfer scenario, you just end up with different values of A in absolute units.
Yeah, I think A is the most important, but R is actually different. One thing you can see is that in this case, it's doing root slope overflow, and this case, like far away from it. And so I should actually put the labels here, but this is like, like a 4 solar radius. And this one is probably a little more stripped with a little hydrogen left. So if it goes back to this, it's like 2 solar radius. So I think that actually contributes to some point of it.
Okay, but maybe it's worth checking, but to me it looks like A, it's a little bit hard to compare, but it looks like A is a little bit larger in the plot above, which means that if the masses,
larger. That's true.
Right, which means if the masses are the same, then the angular frequency of the orbit is lower above. So even if you were perfectly tidally locked, so even if tides were very efficient, you would still have slower rotation in case A than in case B.
Okay, thanks. I should look into that.
Okay, great. If Sylvia can come start setting up, we'll take one more question here.
Ylva Göthberg. So thank you so much, Linhao. That was really interesting. I'm curious about these other two properties that tend to affect the spin of the star, which is like mass loss rate and how you treat angular momentum transport inside of the star. What settings have you used for that?
Okay, the assumption is very simple. Radial rotation plus mass loss removes a specific angular momentum at the surface of the star. So the physical reason for that treatment, well, for angular momentum transport is really not, it depends on what theory you believe, but it's typically, I think most of the evolutionary phases is kind of expected that it remain very radial rotation, part of the reason that you have this strong torque. But I'm not sure about the mass transfer phase because it's really on a thermal time scale that's much shorter. Yeah. And for the mass loss?
Winds, yes.
Winds?
Did you have any winds?
I have. This is 10% sort of metallicity. I have winds. But I think in most cases, these winds are not strong. And in those fast spinning case, you actually have this nuclear time scale mass transfer at the later phase where tides are actually important. And thus this controls the biggest part of the mass loss, not the winds. So I think that is not relevant, not very relevant in that phase. Yeah.
Okay, if you have more questions for Linhao, you'll be able to ask them in just 15 minutes. And let's thank him again.